Hello everyone, myself Girish. I'm here with the SolidWorks simulation session on simply supported beam analysis with point loads, and we'll just validate the same with the hand calculation as well as over the internet. We'll do the same cantilever beam testing, and we'll get the SFT PMD, and we'll just see the results, how exactly it's gonna vary, and how to validate the same. Yeah, so the agenda of the day is first we'll do the hand calculations of simply supported beam, and then we'll cross verify the results over the internet. We're just dealing with the websites of beam deflection calculators. We'll see that one, and we'll again discuss about the shear force diagrams and bending moment diagrams, what exactly they are and how we need to calculate these SFT and BMDs. We'll use a SolidWorks simulation to just deal with this kind of simulations, and we'll again cross verify the results, and we'll have the overall brief discussion about the results. Yeah, about the material, so I'll take the mild steel into account, so that is cotton grade. If you search for the mild steel properties over the internet, you're gonna get the data like this. So there are different grades available. According to that, you can consider anything. So I have taken the density of 8000 and the modulus of elasticity as 210 gigapascal, yield strength 345, and tensile strength as 485 into account. Okay, yeah, so this is the hand calculation. So as you could see here, I have considered the simply supported beam at location A and B. This is a kind of you can see a rectangle with the thickness of 50 and 25, length and width. Okay, and the point load I am applying 200 kgs on these locations C, D, E, F. Okay, the distance, as you could see, from A it is one from A apart from 110 mm. Here I have applied the 200, and from here 310 it is 200 again, from 510 200 kgs, and 710 200 kgs, and total length is 820 mm. Okay, so this is the overall simply supported beam analysis we are considering. Well, the first thing is we need to take the reaction forces at the both the ends, which is equal to the summation of the loading conditions. So this is the equation, that is sum of upward forces which is equal to sum of downward forces. Okay, so if I consider sum of upward forces, there are only two forces, that is Ra and Rp. Okay, and sum of downward forces, if I consider, there are 4 point loads. Okay, that is 200 200 200 200, totally 800, and Ra plus Rp. So this is the first equation with respect to the sum of upward loads and sum of downward loads. Now we'll use the summation of moments into account, and we'll just again deal with the equations to get one more equation to evaluate the both and to get the reaction forces at A and B. Okay, so that is moment at A is equal to 0 I have considered. Now we'll deal with the remaining things. So from here I'm going to consider the moment. So if I'm going to consider the moment along the anti-clockwise direction, I'll take it as a positive one. Okay, and clockwise negative. So this is RB into total distance from the point A is 820. So downwards at C point it is downwards, so the moment will be like this, so negative. Point load is 200 into the distance is how much it is, 2226 and 110 710. Same thing, minus 200 into 22 110 510. Okay, same thing, minus 200 310, and then 200 110, which is equal to 0. Summation of these all the steps, which is equal to 0. And then if I equate this equation, Rp into 820, which is equal to these all the steps, so you can calculate these values, 1,42,000, 1,02,000, 62 and 22,000 divided by 820. If I do, I'll get the Rp value, that is 400 kgs. And if I equate this value here, Ra plus Rb, which is equal to 800 kgs. So if I consider Rb which is equal to 400, Ra which is equal to Rb. Okay. So we got the reaction forces at both the sides. Now we'll calculate the shear force calculations. To deal with the shear force calculation, we're gonna just have the values here. Let's say if I considering this point into account, the reaction force at this location is 400. We know that RB. Okay, so that is totally 400. I'll consider the upward forces into account as positive and downwards as negative. Okay, if it is moving upwards, it is negative now. Okay, sorry, upward loadings are negative and downwards loadings are positive. So here shear force at P location is minus 400, that is RB, which is equal to 400. Okay, and then shear force at C, which is equal to 400 minus 400 plus 200, that is minus 200, and D minus 200 plus 200 and 400, that is 0. At E, if I consider at E, minus 400, 600, that is 200. Same thing at F, 246, right, and then it is 400. 246, so 600 kgs here, and minus 400. If I do it, it should be 200 at E. Yes, that is correct. And at F, if I consider 246 and 800 minus 400 is 400. And if I consider at this location, you already know shear force at A is RE, that is again 400. So these are the shear forces into account which we have considered. And to deal with the bending moment, same thing. Formula is anti-clockwise. I'll take it as positive now. We'll consider bending moment at B, which is equal to 0. That is bending moment is equal to force into perpendicular distance. We know the formula, right? So if I consider this equation here, and if I consider bending moment at B, there is no perpendicular distance, that is 0, right? And now we'll just deal with the bending moment at C. So that is the load is 400, right? It is moving upwards and into distances 110 from point C. So point C, at point C bending moment is 44 kg per millimeter. And then if I consider the D, same thing, 200 and 400 is acting. So 400 is towards clockwise. Okay, it is moving like this. So 400 into distances, perpendicular distance 310. Now I need to consider the point load, that is at C. 200 into distances from D is, it is 200. Okay, and that is what the value here is, 84,000. Okay, same thing at bending moment at E point and F point, you can calculate and get the same values, that is 84,000 and 44,000. Okay, yeah, if I calculate the bending moment at A, it will be 0. You can just simply calculate and cross check the same. So this is about hand calculation, and if I just draw the bending moment and the shear force diagrams, you'll be having the same stuff. Okay, so it is approximately 84,000. This is approximately 400 kgs, and this is the internet equations. You can directly use the website to deal with this one. I'll showcase how to do that one. You can see the point loads. We have applied 2 kgs, matlab, yeah, 200 kgs at each and every points, and this is the total distance. Okay, yeah, this is the again the cross verification of same, and then you'll get these, right? This is the shear force diagram, bending diagram, and when I just validate with the software, this is what you're gonna get. Yeah, now here if you just go to the website, and if you use this free beam calculator, here you can able to specify the length, and 820 mm. Here the Young's modulus, I'll take the 210 gigapascal into account. Cross-sectional area. So to get this value, you can go back to your software, and there you can just use the evaluate tool to check the section properties. So if I click on this calculate, you're gonna get the area 273.7. You can add the same on the software to just cross verify the same. So it will take 274 into account. Fine. So I need to consider the moment of inertia into account. So at this region, I'll take the Iyy into account because it is along y direction, perpendicular distance. So 83,837. Yeah. So now I need to deal with the supports. So support type is pinned at both the locations. Now the point loads. The first load, I'll add it as magnitude. It should be 2 kilonewton, so that will be approximately 200 kgs. And the distance, so at 110 mm, that should place. Second one is again 2 kilonewton. Distance should be 310 mm, sorry. And third one should be at 510, and fourth one should be at 710. Same value in all the regions. So once you define these, you're gonna have the bending moment and the shear force diagrams. In the summary, you could able to see the reactions and the loading conditions and shear force diagrams and the bending diagrams. So if you just deal with the same hand calculations which we have done, if you create the same SFT and BMD, you're gonna get the same shape as you can see here. Well, so this is how you can simply see here. Same thing. The deflection will depends upon the material and the cross section you're gonna deal with. So that will neglect for now. Okay. So well, I'll directly go ahead with the simulation activities now. I'll switch to the SolidWorks software and do the workaround to just get the same with respect to SolidWorks simulation. Yeah, so as you could see, this is the beam I'm gonna take into account. You can see the dimensions as well. So I have taken the same. You can go ahead and you can activate the show annotations so that you can cross check the same. You can see the total length is 820, 710 plus 110, and the distance between the points is okay. So I use the multi-bodies because to consider this into simulation studies, I need to convert into beam. So I have taken into beam analysis here. So I'll create a new study with the simply supported beam analysis. Okay, and I'll convert this particular model into beams. Before that, you could see here these are the different solid bodies which are generated with respect to the multi-bodies. So I'll apply the material first. I'll treat them as beam, so they are converted into beams, and you could see according to that the joints also created, right? And now I'll apply the material. The material should be mild steel. So over here I have defined the same through the internet. I got the data and I entered it manually, and this is what I'm going to consider here into account. Okay, so it is mild steel grade A. Well, once you're done with that, you can simply specify the different parameters like fixtures and loading conditions. Now I'll add the fixture. So while defining the fixtures, you're gonna have the options that is immovable. So this time I'll select the immovable because that is appropriate fixture for the corners joints in the beam analysis. And the loading condition, you can simply select the force into account and automatically the points will be generated. You can simply choose the joints to account, and you can use the top view. Yeah, yeah, you can just define the value here. Can even change the unit system from Newton to kgf. In the metric system, you can able to define 200 kgf, which is equal to 200 kgs. That's fine. Okay, so once you're done with this, the fixtures and the loading conditions are done. I'll simply hide these annotations and this coordinate system. Finally, you can mesh it by using default mesh, or if you want to refine it, you can even refine it by using the additional options. But here I'll simply go ahead with this particular mesh and I'll run the study. Yeah, so you could see this is the axial bending and the resultant displacement time. The factor of safety is 0.94. If you want the beam diagrams, you can simply choose it from here. This is the shear force diagram. You can simply choose along direction 2, and you could see it is as per the what exactly we have seen in network internet. Yeah, so now I do need the bending moment diagram. We can simply delete one of these and I'll edit this one. Go ahead with the bending moment. Unit system we can choose, and here along direction 1 it is not giving. I'll change it to direction 1. Okay, here you could see this is exactly the bending moment diagram which we have got from the validation, right? And this is the shear force diagram. By just switching to the axial and bending stress values, you could see it is more, and the resultant displacement will vary accordingly the boundary conditions and the material we have defined, and the cross section also matters there. We are mainly concerned about the shear force diagram and the bending moment diagram. Yeah, so we have seen that the bending moment and the shear force diagram which we have got from the SolidWorks simulation, and that is closely, or it will definitely match with the whatever the results we have seen from the internet, over the internet, as well as the hand calculation gonna match the same. And here you could see the shear force, it is 400 kgs. That is same as that of the hand calculation we have done. And you could see the shear force diagram here, it is resembles the same. The values are all the same thing. Okay, if I just change the unit system and if I filter your chart options, you're gonna get the same, no issues there. So in the software we have seen that the shear force in the form of Newton, so that was showing different answers. That's okay, you can change the unit system and the flow charts. And coming to the bending moment, so if I just convert it to the kg per kg centimeter, it is the same here. We have got 84,000 actually, so if I convert it to same unit system, we'll be having the same 84,000 only. According to that, this is the same bending chart, you have it. Okay, so this is how you can simply compare the whatever the practical scenario is there, simply supported beam with the hand calculations as well as by using the internet. That is also the best way to deal with this kind of steps. And if you want to validate with the softwares, so that also we have seen, right? And again we have seen how we're gonna deal with the shear force diagrams and bending moment diagrams. So how we need to calculate, if you want the bending moment diagrams, we need to deal with the bending moment, the force which is equal to bending moment which is equal to force into perpendicular distance formula, and shear force if you want to calculate, we need to consider the point load. According to that, you can just get the shear force diagrams. So yep, the result discussion. So we have just verified that what are the shear force and the bending moment diagrams we are getting from the internet, and the hand calculations are is exactly matching with the results we are getting in the SolidWorks simulation. Yep, so this is all about the validation with respect to the simply supported beam with the point loads. Thank you guys, stay tuned.